Welcome to qnawire.
Hi, so over here we're going to have the dissociation of trimethylacetic acid, which has the formula C4H9CO2H. That is going to dissociate when it comes into contact with water into C4H9CO2 minus plus H3O plus. From now on, I'm going to just label this as HA and A minus, just to simplify all of the writing from now onwards. And in this fashion, we're going to be able to find what is going to be the correct result. The other information that is given, not directly in the problem, is going to be the value for the pKa. In this case, the pKa is equal to 5.03, and the initial concentration is going to be equal to 0.22 millimolar. Remember that 0.22 millimolar is the same as saying 2.2 times 10 to the minus 4 molar. Always convert to something that we can treat directly. So in our ice table, over here in my reaction, of course, I'm omitting the fact that we need to put water into it, but we really don't care about the quantity of water since that is going to be a condensed phase, and condensed phases are not going to enter into our equilibrium equations. So the initial amount, I'm going to label this as C0, just for sake of simplicity, 0 and 0. The amount of change minus x, and plus x. At equilibrium, we're going to get C0 minus x, and x. So our value for Ka, which is going to be equal to 10 to the minus pKa, which is 10 to the minus 5.03, would be equal to concentration of A minus, concentration of H2O plus, divided by concentration of HA. This becomes, from replacing our equilibrium concentrations, x times x divided by C0 minus x. Now, notice that the value for the concentration is times 10 to the minus 4. So it may be possible that applying the small x approximation is not a good approach. So let's verify it. Whenever we want to apply the small x approximation, we're considering that the value of x is going to be much, much smaller than my initial concentration. Okay, so if that is true, we will get that C0 minus x would be approximately directly C0. Under that condition, the value for Ka would be equal to x squared divided by C0. Thus, solving for x, we would get the square root of Ka times C0. Let's check if the result satisfies this condition. If it does, then we can proceed and we don't need to solve the quadratic expression. If it doesn't satisfy that condition, then we need to solve the full quadratic expression. So over here, the value for Ka is 10 to the minus 5.03 multiplied by 2.2 times 10 to the minus 4 in terms of molarity. And we would get a value of 4.53 times 10 to the minus 5 mole. Now, if we compare this versus C0, which is 2.2 times 10 to the minus 4 mole, as you can see, the difference is only 1 order of magnitude. And actually, if we divide one by the other, we get that the value for x is 20.6% of that of my concentration. Actually, I think that is why you put 21%, right? So that is not the degree of dissociation of the acid in this case, because we cannot apply a small x approximation. So what we need to do is solve the full quadratic, which reads Ka is equal to x squared divided by C0 minus x. We can expand this, multiply C0 minus x to the left, so we get C0 times Ka minus Ka times x is going to be equal to x squared. Thus, the equation that we need to solve for is x squared plus Ka times x minus C0 times Ka equal to 0. Let's replace the values. X squared plus 10 to the minus 5.03 times x minus 2.2 times 10 to the minus 4 times 10 to the minus 5.03 equal to 0. And the solutions are going to be two different solutions, x1 and x2. You can solve this either in your calculator or you can apply a general formula for quadratic expressions. So the results that we get here are going to be equal to, for some reason it bugged out a little bit, wait a second. We get minus 5 times 10 to the minus 1, 2, 3, times 10 to the minus 5. This result we can already get rid of because it is negative and that doesn't make sense in chemistry. Another one is going to be 4.088 times 10 to the minus times 10 to the minus 5. And this is going to be your correct result. So now we can calculate the degree of dissociation. This is the amount that dissociated. So x divided by my initial concentration times 100, right? So 4.088 times 10 to the minus 5 divided by 2.2 times 10 to the minus 4 molar times 100, we get the value of 18.58% or 18.6%. And this is going to be your degree of dissociation. Notice how it differs when you solve the full equation, the full quadratic expression, with compared to applying the small x approximation. Within the small x approximation, your result would be correct, but as we notice over here, the value is not much smaller than my initial concentration, so that approximation is not going to be valid. So with that, it would be all. Thank you very much and have a good one.